Hey guys, how's everything going? Today, let's take a look at number 1197, minimum night moves. This is one of my videos that I'm going to use to prepare for my Facebook interview in June. So hope it helps myself and I hope it helps you. So we're given an infinite chessboard with the coordinates from infinity to infinity. We have a knight at 0, 0. For each knight, might be 8 moves, right? Yeah. And we need to return a minimum number of moves for the knight to get to the square xy. The answer is guaranteed exists, and the constraint would be, yeah, it's not that big. Well, first let's analyze some basic. The basic idea is just to go to just tame the canvas one step by step, right? Right. The first one is 0. So let's mark the cell with the minimum steps. Okay, from here we have 8 moves, which will be 1 step here, 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 something like this, right? Okay, now let's analyze next steps. Is 2. So the 2 will start with 1, step 1, right? So it would be like 2, 2, 2, 2, 2, 2, and okay, here is 0, and it's smaller than 2, so we skip, and 2, 2. So the picture just came to us that we could just do this uh, over and over again until we match the coordinates, right? But here's the one problem, that if we want to get the point, like get the point size top right, if we do this like expansion of a taint, it would just grow like this. So there's a lot of unnecessary calculation, right? Like if you want to expand the area to here, it's meaningless because our knight is at the top right. So we need to improve this idea. How? Well, it turns to us that the board is completely symmetric. So if we're given some there for each coordinates in a board, there is corresponding 4 board, which means for the knight to go to either 4 of them, the steps are to be the same, right? So if we are given these 3 coordinates, we can just go to this only one. That reminds us we could just try to remove this part and this part, these 3 diagonal area. Would that work? Let's just try to do something more. If we just ignore these points here, will it still suffice? Okay, for 2, for 1, let's try to complete the 1 condition. 1, 1. So here is 2. Oh, okay. This is for this top right diagonal. And now for 2, here will be 3, right? And 3 here. And then 1, 2, 2, 2, 2, 2, 2. Here's 3, and 2, 3, 3. So here, there's a problem here, right? Yeah, we could move 3 from here, 3 from here, 3 get 4 from 3, but actually you see there is 1 here, so actually 2 would be good. All right? Yeah, going back to the original full expansion here. 1, 2, 2, 2, 2. This is the first one, and this one would be 2, 2, 2, 2, 2, 2. something like this for here. For 2 here, it can get to what it can get to this diagonal is 2, of course 2 here, 2, 2, 2, okay, down, and now here it can get a 2. This cannot get directly from top right diagonal, right? And 2, 3, 3, this could be accessed from 2 here. So the problem is the core is here. But what if here? Here, because you can see that the length, the coordinates will be bigger or equal to 2, right? So it cannot be generated from this part or this part. This could be generated by 3, 3, and now for the points here, right? If there's a point that to the left side could lead to the cell here, there must be a corresponding coordinates to this part and generate to that. So we can forget about it, right? Yeah, the core problem is this two. We cannot generate it because either if you analyze the first one, you see that the originally here, actually the row and the column, actually there's these 4 cells that could not be generated with one step. So actually, if we do it with one more time, and we can cover that, right? That means for the first 2 steps, we need to get all the coordinates, and then from that we could just keep the only positive integers. And there's another problem is that there are a lot of duplications, right? Like these 3 could be generated from these 2, and these 3 could generate also these 2, these 2. So there's we need to keep track of it is already accessed or not. If it already accessed, we will ignore that. So if this 3 is already handled, the next time we will meet again, we need to skip. So the idea, it becomes clear, is that well, first we use a flag, use a map to keep track of the visited or not, right? Okay, we use visited, create a new map, and then we do iteration on each step. I mean it just how should I interpret this? Which means keep track of the cells which could be led to by nth step. But for these, we use a queue. Yeah. And so while there's it should be initialized with 0, 0. And so we need to do this forever while true. What we do here is that first we need to check if we get all the elements, right? And then push the next round of elements in. Check ith nth round points, then push in next round. Of course, we need to keep track of the step. So for each step, we shift the elements out and then push the elements in. But when do we stop? We need an identifier to do that, right? So we use push a null in as an ending identifier. So let's the head. While head equals to Q shift. This while loop will end at this null, so it's gonna be okay. After we check this, and then we need to update the step, right? And then the next step is if it is target. So if 0 equals x, this target will return the step, and it's done, right? And then we need to process next round. We just need to push into the queue, and there are 8 directions. We will define the directions. Well, this is simple. It should be 2, 1, 1, 2, minus 1, 2, minus 2, 1, minus 2, minus 1. Yeah, this is the directions. So for each direction, the next point would be this is the next point, right? If this point is not accessed, we can push it in. So it should say if visited has a key would be next 0. If it's already visited, oh no, wait a minute. If it is not visited, we could push it in, right? So the queue would push the next. And then we push all in, and we update the step. It seems all right. But remember, but there's a problem that for each round, for this 0, right? We push this in, and then there might be 2 different cells have this duplicate next round cells, right? So when we shift, we would add. Oh, wait a minute. I forgot. For each head, we should set it to accessed. So the key would be visited set key true. Even we do this, there still might be duplicate elements be pushed in because they are not accessed yet. So we need to do the check here. If it is already checked, we continue, right? Skip this, and then we do everything. Yeah, this seems right. Let's try run code. Cool. The simple one is work. Let's looking for 5. Cool. Let's submit. You see, I didn't accomplish it with one pass. I tried a lot of times. There are time that exceeded wrong answer. So actually we were accepted, but we're not that fast enough. As we analyzed before, for within the 2 steps, we need to keep track all the node except only is the special case is these 2, right? So after step 2, we only keep the positive cells and it will suffice. Yeah, let's try to do that. So the first thing we used to normalize the input. X would be math abs. We took the top right points, and then we only pushed it in. Only push in the unvisited and the positive ones. And step is could be smaller than 2, but after step 2, all of them should be positive. Non-negative, I mean. Let's try to run the code. Unexpected token. What? If has and here. Cool. This should be right. Unexpected. Huh? What? Wait a second. This should should be right. Okay. And then it should be step, it should be bigger than 2. And next 0 is bigger than 0. And next 1 is bigger or equal to 0. Cool. Let's submit again. Yeah, we're much faster than that. Okay, so what's the time and complexity of this algorithm? What time? Time. Well, it's hard to say. Well, it's really hard to say for each batch steps. Wow, I really don't know. What's the time complexity of this one? Let's do some simple analysis. While true, while head. Every time we pop an element out, we pushed 8 in. Worst case, 8 in, but there are a lot of duplicates. And we've reduced at least 25%. But the time complexity, would time complexity change? 8 every time 8, so for so anyway, so wow, I don't know, because we're getting the coordinates, actually the steps. Let's say the step, let's say n step, and we wow, it's 8 to the n. I don't know. For space, we use a map to keep track of the visitor node, and that would be, oh, this we know. This because we only took the top right area, so it's something like this. Of course, suppose a, x, y are non-negative. Here's something. As we do our analysis, actually the expansion will cover more and more elements, right? So actually, how many for each cell? I mean, for each cell, we would check constant 8 times for next coordinates, and the next coordinates actually each cell will actually be traversed once. So it's actually big O x to y to check each cell. For each check, we might cost 8 rounds. And all the check are all the check all the check are using this hash table, so it's constant. The maximum is like 8, right? So it's the same as the space complexity. Maybe I'm wrong. I don't know. But if I'm asked, I will say something like this. Okay, so that's all for this problem. I hope it helps. Well, I learned a lot. I learned a lot from this problem. The traversal, which is actually breadth first search, and then we try to improve this algorithm by reducing unnecessary calculation. Wow, cool. So okay, see you next time. Bye bye.